Good evening, students. You're able to hear me?
Yes, sir.
Okay. So shall we get started with the next chapter, that is probability? I think this is the last chapter left out, right? In your math. Yes or no?
Yes,
So
sir.
just wanted to find out, after this chapter, is there any chapter that you want a recap of? Any chapter that you feel that is tough? Nothing.
Sir, could you recap trigonometry?
Trigonometric equations or complete thing? Trigonometric equations are right? Fourth exercise, 3.4. I think that is the only thing
Yes,
you
sir.
have. Yeah, that I can do. Anyways, shall we get started? So this thing, probability, right? The concept of probability is not something new to you. I've been dealing it from your lower grades. So what is that you know about probability? So basically, if somebody asks you what is the probability of something to happen, what will you say? You will define something like this. It is defined as the number of favorable outcomes divided by the total number of outcomes. Is that right? So this is how you define, if I'm not wrong. Correct? Right. So here we are going to talk about an important condition called, generally you measure probability for experiments. Right? You do an experiment, and if you have to give a simpler explanation of why probability is useful, can someone tell me why do we even calculate probability? Let it be known, why do we need to do the probability? It has a very important role or very important significance. What is it?
Sir, we came to know about the chances for an event that may or may not.
That's right. So mainly it is used for the concept of success and failure of something. You're doing an experiment. There is a possibility of success and there is a possibility of failure. If you're just interested to calculate, let's say, what percentage of success is possible for that particular event to be, what percentage of success is possible for a particular event, then we go with the concept of probability, right? So generally, when you perform an experiment, there are two kinds of experiments that you can perform. What are they? One is called as deterministic experiment, and the second is called as random experiment, right? So as the name suggests, deterministic means what? As the name itself is suggesting, what do you mean by deterministic? Means you surely know the output of a particular experiment, right? So if I ask you what is the probability of a deterministic experiment, what will you say?
1.
It is 1. It is 100%. So if you multiply that 1 with 100, 1 is a fraction. Like probability is generally a fractional value. If you multiply that with that with 100, that will give you the percentage of something. So it deterministic means you are 100% sure that this is what is going to happen. So there is no point in talking about probability for a deterministic experiment for which we already know what is output, right? So that is why we are going to concentrate on random experiments, right? So in a day-to-day life, we perform many activities which have a fixed result no matter any number of times they're repeated. For example, given any triangle, without knowing the three angles, we can definitely say that the sum of measure of the angles is 180 degrees. Correct? So similarly, this is a deterministic experiment. If I give you an experiment where I'm asking you to calculate the sum of sides of a triangle, even without doing it, you can say it is 180 degrees. So it's a deterministic experiment. But there can also be So it also says we can perform many experimental activities where the result may not be the same when they're repeated under identical conditions. For example, if you take a coin and you keep tossing the coin, is there a possibility for you to say that every time there'll be head? though you're doing the same experiment under the same identical conditions? The answer is no, right? It can either turn up as head or tail. So what is the percentage of a particular happening in that event? So what is the probability of you getting a head? It is half, and the probability of you
50%.
getting a tail is also, it is 50% chance, right? 50-50. But we are not sure which of these results will actually be obtained. Such experiments are what are called as random experiments. So basically, we are concerned more about random experiments. So in the first exercise, if I have to speak in terms of exam point of view, the first exercise, we are concerned about writing all the possible outcomes within a set, and that set is given a name called as sample space, right? So an experiment is called random experiment if it satisfies the following two conditions. What is it? It has more than one possible outcome. Secondly, it is not possible for you to predict the output in advance, right? So check whether the experiment of tossing a die is random or not. Answer is it's a random experiment. In this chapter, we shall refer the random experiment by experiment only unless it is stated otherwise. So wherever you use the word experiment, we use it only for random experiments. So for an experiment, there is something called as an outcome, and that outcome can be represented in the set form, and that is what is called as the sample space. So what is basic definition of an outcome? A possible result of a random experiment is called as an outcome. For example, if you consider the option of rolling a die, if you have an experiment of rolling a die, the outcomes of the experiment are 1, 2, 3, 4, 5, 6. If you are interested in the number of dots on the upper face of the die, then you write the set of outcomes as what? 1, 2, 3, 4, 5, 6. If I have to write it in the roster form in a set, then this is what is called as a sample space. Correct? Thus, the set of all possible outcomes of a random experiment is called as a sample space associated with the experiment. Sample space is generally denoted by the symbol S. Okay. So each element of the sample space is called as a sample point. In other words, each outcome of the random experiment can also be called as sample point. So as I mentioned, our only job in this exercise is to write the sample space. Means they will give us the experiment. For that experiment, we need to write all the possible outcomes. Shall we start?
Yes, sir.
Right. So there are two coins, a 1 rupee coin and a 2 rupee coin, which are tossed once. Find the sample space. So whether you talk about a 1 rupee coin or a 2 rupee coin, both have head tail and head tail. Correct? So if your concern is only about head or tail, you're not concerned about whether it is a 1 rupee coin or a 2 rupee coin. Right? So then you would have spoken about these things. So what are all the possible outcomes? You can get head on the first coin, head on the second coin. Or you can get head tail, or you can get tail head, or you can get tail tail. So there are 4 possible outcomes. Is that clear? Right. Suppose I extend this to 3 coins, then how will you write the sample space? Suppose 3 coins are tossed at once, then I ask you to write the sample space, the possible outcomes, then how will you write them?
Sir, head, tail, like that.
Like that. So it is very simple. Okay. If it is 3 coins, can you tell me how many elements will be there in the sample space?
8.
How did you get that 8? So
Sir, 2
a
to the
coin,
power.
yes, a coin has 2 possibilities, and 3 coins, 2 to the power of 3. So out of this 8, what you will do is first write like this: head, 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 tail, 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 tail. Then what you will do? Head, head, tail, tail, head, head, tail, tail. Then you'll write head, tail, head, tail, head, tail, head, tail. So if you put everything within a bracket and write it in the horizontal form, that becomes the sample space. Did everyone understand how I wrote it? So this 8 is there, no? I broke them into 2 parts. 4 heads, 4 tails. In the next column, 2 heads, 2 tails. So 4, I made it half. 2 heads, 2 tails, 2 heads, 2 tails. In the next column, I made this 2 as half, 1 head, 1 tail, 1 head, 1 tail, 1 head, 1 tail, 1 head, 1 tail. Clear? So find the sample space associated with the experiment of rolling a pair of dice. One is blue and the other is red once. Also find the number of elements of the sample space. So each die has 6 possible outcomes. And how many dice are rolled? They are 2. So 6 power 2 will give you 36 outcomes. And what are those 36 outcomes, guys? And what are those 36 outcomes? So if you draw a box like this, 6 and 7. Okay. So this 1, 1, 2, 3, 4, 5, 6. Or I'll start from here. 1, 2, 3, 4, 5, 6. And here I'll start 1, 2, 3, 4, 5, 6. Right. 1 and 1. So 1 comma 1 will be one outcome. 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 6. So in this, is the order important? 1 comma 6 and 6 comma 1. Are they both the same?
No, sir.
No. Right, because in the first place they are 2 different dice, and the ordered pair is also written in such a way that these are the possible outcomes. So 1 comma 1, 1 2, 1 3, 1 4, 1 5, 1 6. Similarly, you will start with 2. 2 from here, 1 from here. So 2 comma 1, 2 comma 2. It keeps on going till 2 comma 6. Then 3 comma 1, 3 2 till 3 6. 4 1, 4 2 till 4 6. 5 1, 5 2 till 5 6. 6 1, 6 2 till 6 6. Right. So there are 36 outcomes that are possible. If you're not clear at any step, please stop me. In each of the following experiments, specify appropriate sample space. A boy has 1 rupee coin, a 2 rupee coin, and 5 rupee coin in his pocket. He takes out 2 coins out of his pocket, one after the other. So our job is to write sample space. So how to start? How to write? So I'll use O for 1 rupee coin, T for 2 rupee coin, F for 5 rupee coin. So when he's taking in a proper one after the other, right? When he's taking one after the other, then what are all the possible results? So how will the sample space look like? He can take the 1 rupee coin first, then 2 rupee, 1 rupee and 5 rupee. Or he can take 2 rupee and 1 rupee and 2 rupees and 5 rupees. Or he can take he can take 1 rupee. What else can he do, guys?
So
Or he can take
FTFO.
FO and FT. So there are totally 6 possible outcomes. So how to use the knowledge of permutations here? So he has 3 coins. So he is taking them in an order. Order is like arrangements. Out of the 3 coins, he's taking 2 coins and arranging them. So 3p2. So what is 3p2? 3 factorial. Oh, there should be 6, right? So he's choosing 2 coins.
Sir,
1 minute, 1 minute.
denominator should be 1 factorial.
Now 1 factor, that's what I was wondering. Yeah. 3 factor n factorial divided by n minus r factorial. So 3 factorial is 6. Now you got, that is why we have 6 outcomes. Is it clear? So why did I use permutation here? Because one after the other is what they mentioned. They didn't say he's choosing something at random. Next, a person is noting the number of accidents along a busy highway during an year. A person is noting the number of accidents. So this is going to be a sample space of infinite length, right? So there's an infinite set. So throughout the year, when he's writing down sample space, there's uncertain, right? There can be 0 accident, 1, 2, like this, it can keep on going. We don't have a number. Example 4. There is a coin which is tossed. If it shows head, we draw a ball from a bag consisting of 3 blue and 4 white balls. If it shows tail, we throw a die. Describe the sample space of this experiment. So what is there? There is a coin which is tossed. If it shows head, we will draw a ball from a bag consisting of 3 blue and 4 white. So head comes, you can choose a ball, right? You can choose blue ball, which is 1, or you can choose blue ball, which is 2, or you can choose blue ball, which is 3. Or you can choose white ball 1, HW2, HW3, HW4. This is what happens when the head comes. Whereas when tail comes, what will happen? T, you will roll a die. T, 1, sorry, T1, T2, T3, T4, T5, T6. So since here the order is important, I wrote the T first and then 1 next. Example 5. Consider the experiment in which a coin is tossed repeatedly until a head comes up. So repeatedly until a head comes up means a sample space is again infinite set. We don't know when head will come. So maybe he got it for the first time itself, or first time he would have got tail, then next time he could have got head, or he could have got tail, tail, head, or he could have got tail, 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 head. It keeps on going like this. So it is an infinite set. I hope I'm clear, right? So tell me one thing. Do you want me to solve this exercise or you already have done it? Shall I move on to the next part? Or you want me to solve it? You guys tell me. What should I do? Fast.
So
Should I
you can
solve?
move to the next one.
Move to the next one. Right. Next definition that we are going to concentrate upon is an event. So what is an event? We have studied about random experiment and sample space. So random experiment is the one for which you don't know the output, and sample space is all the possible outcomes. Right? You write it in a set form associated with an experiment. The sample space serves as universal set. Since we are using set, that is a universal set for all questions concerned with an experiment. So consider the experiment of tossing 2 coins and an associated sample space with it is head, 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 tail, tail, tail. Sorry, tail, head, and tail, tail. Now, suppose that we are interested in those outcomes which correspond to the occurrence of exactly 1 head. What did they say? Now we are interested in those outcomes which correspond to the occurrence of exactly 1 head. Then we can write head, tail, and tail, head are the only elements from the sample space which are the favorable outcomes. Right? So then, or the only elements of S corresponding to the occurrence of this happening, and the occurrence of this happening is what is technically called as an event. Then if you write these 2 elements, which are the favorable outcomes in a set form, then that is the one which are the events which are possible from the given sample set. So from this, we can conclude in terms of set language, we can say that the set E is the subset of the sample space S. Similarly, we find the correspondence between the events and the subset of S. Is that clear, guys? So if I have to describe the events, then the corresponding subset of S. So suppose the same 2 coins, you're describing an event like this. Number of tails is exactly 2. Then there is one possible outcome. What is it? TT. So generally, any event is represented in the uppercase, right? Which is going to be taken from the sample space. Number of tails is at least 1. So at least 1 means it can be 1 or 2. So head, tail, head, and tail, tail. Number of heads is at most 1. So maximum heads that are possible should either be 0 or 1. So head, tail, 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 or it can be, head, head, tail, tail, head, or it can be tail, tail also. So what is the difference between utmost and exactly? So utmost means it can be either 0 or 1, and exactly means it should only be 1. Then the tail, tail would have not come. Second toss is not head, is an event. Second toss is not head means the second space should be occupied by tail. So it can be head, tail, or tail, tail. Number of tails is utmost 2. Utmost 2 means number of tails can either be 0, 1, or 2. Means it is a complete sample space. So we know that the sample space itself is a subset of itself. Sample space is a subset of itself, right? So number of tails is more than 2. So it is going to be a null set. So the probability of that kind of an event is 0. So the definition is any subset E of a sample space S is called as an event. That's it, mathematically. So there are two things: occurrence of an event and types of event. So what is the occurrence of event? If you consider the experiment of throwing a die, let E be an event which is associated with a number less than 4 appears. Then can you tell me the event, guys? So what will be the event?
1, 2.
1, 2, 3.
1, 2, 3. Right. If actually 1 had appeared on the die, then we say that the event E has occurred. As a matter of fact, if outcomes 2 or 3 occurs also, we can say that the event E has occurred. Then the event E of the sample space is said to have occurred if the outcome omega of the experiment is such that omega is a subset of E. Omega means this 1 is omega, 2 is omega, 3 is omega. If the outcome omega is such that omega doesn't belong to the event E, then we can say that the event E has not occurred. Means occurrence of 4, 5, 6 does not belong to this set. Right. So from this, if you classify the types of event, then the events can be classified into various types on the basis of the elements they have. One is impossible and sure event. So what is an impossible event? The empty set phi and the sample space S describe the events. In fact, phi is said to be an impossible event. For example, when you toss 2 coins, the impossible event is for you to get both the tosses, for you to get more than 2 tails is an impossible event because you have only 2 coins. Whereas the whole sample space is called as a sure event. Sure event means number of tails is at most 2 is a sure event. So to understand this, let us consider the example of rolling a die. The associated sample space is 1, 2, 3, 4, 5, 6. Let E be the event. Then the number appears on the die is a multiple of 7. Is an impossible event. Right. Now let us take up another event if that the number turns up is odd or even. So when I say odd or even, the number can be 135 or 246. So when you write it in the set form, it is the sample space itself. So this is a sure event. Clear? Then we have something called as simple event and compound event. So what is a simple event? If an event E has only one sample point, then it is called as a simple or elementary event. So in a sample space containing n distinct elements, there are exactly n simple points. For example, in the experiment of tossing 2 coins, you get the sample spaces head, 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 tail, tail, head, and tail, tail. There are 4 simple corresponding to this sample space. There are 4 simple events. What are they? Head, 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 tail, tail, head, and tail, tail. Clear? So if you take only one element from the sample space and you call it as an event, that event is termed as a simple or an elementary event. Now, what is a compound event? If an event has more than one sample point, it is called as a compound event. For example, in the experiment of tossing a coin thrice, E is an event which has exactly one head appearing. Exactly one head means head, tail, 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 head, tail, or tail, tail, head. So both the times there should be tail, and one time it should be head. So head can either be the first toss, second toss, or third toss. At least one head appeared. So at least one head appeared means there can be 0 heads or 1 head. So sorry. At least one head means there can be 1 head, 2 head, or 3 heads. So head, tail, 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 head, tail, 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 head. That is where one head is appearing. Similarly, head, head, tail, head, and tail, head, head. That is the event where 2 heads are appearing, and head, head, head. That is where the event of the sample point has all the 3 as heads. So at most one head appeared. At most one head means either 0 heads or 1 head. So tail, 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 head, tail, 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 head. These are all the possible outcomes. Right. Next is, I hope you're clear with the types of event, right? So you know what is an event? What is a simple so what are impossible and sure events? You know what is a simple event, and you know what are compound events. Clear? Any doubt? Okay, so I'm proceeding. Now we'll be dealing with the algebra of events. So we are going to take the knowledge that we gathered in sets and we are going to apply it here. In chapter on sets, we have studied about different ways of combining 2 or more sets, that is union, intersection, difference, complement of a set, etc. Likewise, we can combine 2 or more events by using the analogous set notations. So how are you going to use this? Let A, B, C be events associated with an experiment, and that experiment has the sample space as S. So what is the complementary event? So for any event A, there corresponds an other event A dash, which is called as the complementary event to A, which is also called as not A. Means if A has occurred, then you can confidently say that A dash has not occurred. Okay. So let's take an example to understand. For example, take the experiment of tossing 3 coins. An associated sample space is head, 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 tail, tail. Sorry, head, head, tail. So there will be 8 elements: 1, 2, 3, 4, 5, 6, 7, 8. I already told you how to write those 8. There be an event A, which is head, tail, head, 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 tail, and tail, head, head. So what is this event? So this is an event where you can say there is only one tail that has appeared, or exactly 2 heads are there. Okay. Then if I have to write A dash, then what are they? So A dash is what?
Sir, head, head.
Ah. Head, tail, tail.
Head,
Tail, head, tail.
tail.
Tail, head, tail, head, and tail, tail. So 1, 2, 3, 4, 5, 6. So event A has 3 elements. Event A dash has 5 elements, such that the number of elements in A plus the number of elements in A dash will give you the number of elements in the sample space. Is it not right? So, are you able to understand?
Yes, sir.
Right. So I just want to derive a formula here. Number of elements in A plus the number of elements in A dash is equal to number of elements in S. Okay. So if I divide it with the number of elements in the sample space, then what does the number of elements in A divided by the number of elements in sample space will give us?
Probability of event A.
This is the probability of event A plus this will give you the probability of event A dash or A complementary, which is equal to 1. So what I'm trying to say is, if you know the probability of an event A to occur, then you can find the probability of the event A to not occur by using 1 minus P of A formula. Any doubt? Second, the event A or B or itself means union. Have that in your mind. So recall that union of two sets A and B is denoted by A union B, contains all those elements which are either in A or in B or in both. So what will you do? You will combine all the elements and write a big set, right? So when the set A and B are two events associated with the sample space, then A union B is the event either A or B or both. So this event A union B is called as A or B. Therefore, event A or B is written with the notation A union B, where A is an event and B is an event. So what is the event A and B? So it is basically A intersection B. That's it. So and means intersection, union or means union. Okay, let us take examples and try to solve them. If A and B are two events, then the set A intersection B denotes event A and B. Okay, what are they trying to say is A intersection B is in such a way that the elements of A, that omega, if you take as an element, that element will belong to both set A and set B simultaneously. So, yeah. For example, in the experiment of throwing a die twice, let A be the event of score on the first throw. Sorry, wait. A be the event. So A is equal to score on the first throw is 6. So A is 6, 1, 6, 2, 6, 3, because two dice are thrown. Sorry, same die is thrown twice. 6, 6. Are you able to understand what I'm trying to say? So this is the event A. Event B is the sum of the two scores is at least 11. So sum of two scores is at least 11 means what will you get? The minimum number you can start with is 5. 5, 6, 6, 5 and 6, 6. Correct? Then if I have to write A intersection B, so the event A and B to occur, what will you do? It is 6, 5, 6, 6. Purida. If I have to write A union B, then what will I write? 6, 1, 6, 2, so on till 6, 6. To this, what should I add? I should add
5,
6. So that's it. Right. So I hope you are clear. The event A, but not B. So event A should happen and B should not happen. So A intersection B dash is the same as A minus B. Okay. So with this knowledge, are we ready to solve problems from this exercise? So 6th. Tell me.
Can't it be like A union B dash?
No, A but not B means A should happen, but not B means A should happen, B should not happen. Okay, A and B are two separate events. So in that, they read the word clearly. A but not B means B dash. Means A and B dash should happen simultaneously. That is the meaning.
Okay, sir. A must happen. Okay.
A must happen, B must not happen. Must. That's another B dash.
Okay, sir.
Okay. So consider the experiment of rolling a die. Let A be the event of getting a prime number. So first, let me write the sample space. I'm comfortable to start like this. So whichever problem is given, right? The best practice is always write the sample space. Now write the event A. Event A is getting a prime number. So what are the prime numbers? 2, 3, and 5. And B is an event of getting odd number. 1, 3, 5. Write the sets representing A or B. A or B in another. A union B. So A union B is how much? 1, 2, 3, 5. Yeah? 1, 2, 3, 5. A but not B in another. A intersection B dash. So I'll write B dash. So what is B dash? We can write in both the methods. I'll tell you. 2, 4, 6. Correct? So what is there in A and what is the common point in A and B dash? It is 2. Are you able to understand what I'm trying to say?
Yes, sir.
So not A. Okay. I forgot something in between. The A and B. A and B is what? A and B is A intersection B. 3, 5. Correct? Not A. That is A complement is 1, 4, 6. Right? So this is how you write. These are all very simple things, guys. So if you have the basic knowledge of sets, you are just applying it in probability. Okay, not a big deal. I hope it is simple, right? Till this point, you guys can handle it. Tell me an yes or no.
Yes, sir.
Right? Now comes the next challenging thing: mutually exclusive and exhaustive events. So mutually exclusive. Let's see what is it. If you have an experiment of rolling a die, then what is the sample space? Sample space is 1, 2, 3, 4, 5, 6. So consider event A, which is an odd number, appears, and event B as an even number appears. Okay. Clearly, the event A excludes the event B and vice versa. What is the meaning of this? I want to know. What is your understanding? So clearly, I'm concerned about that statement. What are they trying to say? Clearly, the event A excludes the event B and vice versa. Abhina, what is it?
They both are complements.
You can say complements, and more precisely, I'm trying to say if A is going to happen, you're surely saying B will not happen. Correct only. What you told is right only. And I'm trying to give a more depth to it. So if A can happen, B cannot happen simultaneously, not even a sample point from B, and vice versa. In other words, there is no outcome which ensures the occurrence of A and B simultaneously. That word is important. Means A and B cannot occur simultaneously. Right? So can I confidently say, if I have to tell it in statement that A and B cannot occur simultaneously, then can I write it in mathematical form as the intersection of A and B is a null set. So they are obviously disjoint sets. So when you draw a Venn diagram, A and B will never join. They are disjoint sets. Right? In general, two events A and B can be called as mutually exclusive events if occurrence of any one of them excludes the occurrence of the other event. To put it in simple terms, the sets A and B are supposed to be disjoint sets. So what is the condition for the events to be mutually exclusive? The intersection of those two sets, the intersection of the events should be a null set. Okay. So now let's see. In the experiment of rolling a die, if you consider the event A as an odd number and event B as a number less than 4 appears. So write down the set A. Odd number 1, 3, 5. Set B. Number less than 4 appears. 1, 2, 3. So A intersection B, if you take, what are you getting? 1, 3. So since A intersection B is not a null set, you can say these two are not mutually exclusive events. Means one is not preventing the occurrence of other. Clear?
Sir?
Please tell me.
Sir, in mutually exclusive event, is the event should not happen simultaneously, or the sample space should not be
No,
same?
sample space. This is not sample space. Don't get confused. This is sample space. Sample space is total number of outcomes. So this is the set for event A. The sample space is don't use that word. Okay. So set when you're writing that the possible outcomes, favorable outcomes in Solomon. So when you're doing something, you're concerned about certain outputs. See, for example, you're playing a game. Let's say you want to climb a ladder now, you will expect a 5. So that is a favorable outcome, what you're expecting. So on the expect பண்றது ஒரு ஈவென்ட் சொல்றாங்க. So if you put it here, right? If you put it here, then these two are different events. Events na meaning another. Suppose you and me are playing a game. Okay. So we both are playing a game in such a way, my coin is in a position where I will be able to climb the ladder if I get an odd number. Nitish, are you able to understand what I'm trying to say?
Yes, sir.
So ladder, na, the snake and ladder game is what I'm trying to talk about so that you can relate. So I'm rolling a die with an expectation of what? With an expectation of
Odd number.
me expecting an odd number. So my ladders are in such a way that even if I get 1, I will climb the ladder. 3 vandalum climb the ladder. 5 vandalum I climb the ladder. Okay, but your position of coin is in such a way that you are expecting 1 or 2 or 3. Means the ladders are subsequent positions there. So your favorable outcome, what you are expecting, is written here. B. That is event B. My favorable outcomes are here. That is the event A I'm expecting. Is my event and your event an exclusive event or not? This is this.
Sir, it is not.
It is not, because we both are wishing something to happen which is common. So I'm wishing to get odd numbers 1, 3, 5. You are wishing to get 1, 2, 3. But we have a common point in expectation. What are the two numbers in common?
1.
1 and 3.
Yeah.
Correct? So that is why our events are not exclusive. Frida.
Yes, got it.
Yeah. So next is exhaustive events. Exhaustive na making use of everything. That is the meaning. So when will you say you're exhausted? You lose all your energy, right? So similarly, exhaustive events and another. If you have set of events and those events are in such a way that they have exhausted the complete sample space, then you call them as exhaustive events. Let us take an example. Let's not directly jump into conclusion. So let us consider the experiment of throwing a die. We have a sample. So when you throw a die, what is the sample space? What are all the possible outcomes you can get? 1, 2, 3, 4, 5, 6. Right. So I am defining an event. So I am expecting in that particular game, whatever game it is, I'm expecting I will be able to win if I get any number less than 4. So what will be the set? What will be the possible numbers I can expect? 1, 2, 3. So B. So second person is expecting a number greater than 2 but less than 5 should appear for me. So what is his expectation? His or her expectation? They want 3, 4. And there is another person playing with us. So that person is expecting the number to be greater than 4 to appear, 5, 6. Are you able to understand this? Right. So these are the expectations. Now, if I take the expectation of person A and person B and I try to find the union. Union, either this can happen or this can happen. If I find the union, is the expectation completely exhausting the sample space? So if I use A union B, what will I get? 1, 2, 3, 4. But what is the sample space? What are the possible outcomes? 1, 2, 3, 4, 5, 6. So event A and B put together are not exhaustive, because there is a possibility of 5 or 6 also to occur. Seriya? Suppose I take B union C. So B union C, tell me guys. So what is B union C? 3, 4, 5, 6. So B and C, can I put them together and say that they are exhaustive events?
Yes.
No, because 1 and 2 is also possible to occur. But if I take A union B union C, then what will I get? I'll get 1, 2, 3, 4, 5, 6. So A, B, and C, all the 3 persons put together who are playing the game, their events are in such a way that all the possible outcomes from the sample space are exhausted. Okay. So, like if you look at that word exhausted and English meaning, it will be slightly complicated. I'll put it in simple terms. If there are 3 events, and for those events, if you take the union, and if the union of all those events put together is a sample space, then you say that the events are not mutually, then the events are exhaustive. So use the word mutual only for exclusive. Okay, mutually exclusive, then the intersection should be a null set. Whereas if you want them to be exhaustive, what should happen? The union of everything should be a sample space. Clear?
Yes, sir.
Right. So there are certain possibilities where the events can be mutually exclusive and exhaustive. Can you give me an example? Can you give me an example where the events are satisfying both mutually exclusive and exhaustive concept? With the same example of die. So for a die which is rolled 1, 2, 3, 4, 5, 6 is a sample space. Right. I want you guys to define an event A and B such that they are simultaneously mutually exclusive and exhaustive.
Sir, at least 4 and less than 4.
So more simpler is odd number and even number. That's it. 1, 1, 3, 5. So 1, 3, 5 and 2, 4, 6. So are they exclusive?
Yes,
Are
sir.
they exhaustive? Yes. So like how Suprajit told, it can either be 1, 2, 3, 4 less than 5 and greater than or equal to 5, 5, 6. These two are also mutually exclusive and exhaustive. Right. That's it. So example 7 is you have 2 dice and those 2 dice are thrown and the sum of the numbers which come up on the dice is noted. Let us consider the following events associated with the experiment. So event A is in such a way that the sum is even. So when you throw 2 dice, you're expecting the ordered pairs to be in such a way that the sum of the numbers in that ordered pair is always giving you an even number. So we know that sum of 2 odd numbers is an even number and the sum of 2 even numbers is also an even number. So what are all the possible outcomes? 1, 1, 1, 3, 1, 5, 2, 2, 2, 4, 2, 6, 3, 1, 3, 3, 3, 5, 4, 2, 4, 4, 4, 6, 5, 1, 5, 3, 5, 5, 6, 2, 6, 4, 6, 6. Did you guys understand?
Yes, sir.
Yeah. Similarly, the sum is a multiple of 3. The sum is a multiple of 3. So what are all the possible outcomes? So the least multiple you can get is 3 and the highest multiple you can get is 36. So 3, 6, 9, 12, 18, 24, 27, 30, 33, 36. Oh, sorry, not 36, 12, no. Did you understand what I meant? So 1,
Yes, sir.
1. So 1, 2 is there, right? If you add 1 to 2, you'll get 3. So that is the least multiple you can get. What is the highest multiple you can get? You add 6 to 6, you will get 12. So that is the highest multiple. So you should choose the numbers which will give you 3. So for you to get 3, 1, 2 and 2, 1. 1, 2 and 2, 1 are different. Similarly, we are done with 3. For 6, what should you get? 1 should be added to 5 and 5 should be added to 1. 2 should be added to 4 and 4 should be added to 2. 3 should be added to 3 itself. Right. So we are done with 6. 9, what will you get? 9, the minimum number that you can start with is 3. Yeah? So 3,
Yes,
6, 6, 3, 4, 5, 5, 4. That's it. You will not get anything else because it's an odd number. Similarly, 12. So for 12, you will get 6, 6. So those are how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So all the elements are written. The sum is less than 4. So sum is less than 4 means 1, 1, 1, 2. That's it. 1, 1, 1, 2, and 2, 1. The sum is greater than 11. Sum is greater than 11 means only sum that is possible is 6, 6. Now they are asking which of these events are mutually exclusive. So for them to be mutually exclusive, the intersection between those two events should be a null set. Tell me, you guys tell me.
C and D.
If I take between A intersect A and B, no. B and C, no. C and D, they are exclusive,
Yes, sir.
right? Only C and D are exclusive. Is everyone clear? Is everyone clear this? Example 8. So there is a coin which is tossed 3 times. So possible outcomes: head, 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 tail, 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 tail. So I always write down the outcomes first. I am comfortable, as I told you. I'll first write down the sample space and then only proceed to read the question. Tail, head, tail, head, tail. Okay. Consider the following here. A is no head appears. No head appears means A is equal to. So what is the event A? Tail, tail, tail. Exactly one head appears. So what is the event B? Exactly one head na. This one, and this one. So head, tail, 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 head, tail, 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 head. What is C? At least 2 heads appears na. It can be 2 or 3 also. At least 2 heads na. Head, head, tail, tail, head, tail, head, head, and head, head, head. Correct? Now, do they form which one? At least 2 heads. Okay. Do they form mutually exclusive and exhaustive events?
Yes, sir.
They are exclusive. So all the 3 put together, A union B union C, it is going to give you the sample space. So it is exhaustive, no doubt in that. Similarly, A intersection B intersection C, what is it going to be? It is a null set. Because nothing is common. All the 3 are different sets. So they form mutually exclusive and exhaustive events. Anyone having a doubt on this? Anyone having a doubt?
No, sir.
Okay. So 16.2, let's do 2-3 problems. Remaining things you tried. Just tell me one thing: is 16.3 taught in your school? Did they teach it?
Yes, sir.
I think yeah, it is needed because we didn't touch probability at all till now. We are only talking about events, so that we can finish it up. Not a big deal. So there is a die which is rolled. Let E be the event. The die shows 4. E be the event where die shows 4, and F be the event where die shows even number 2, 4, 6. E and F are mutually exclusive. No. Common, no. It is not. Second, a die is thrown. Describe the events. A is number less than 7. So it's a sample space 1, 2, 3, 4, 5, 6. B is a number greater than 7. It's a null set. C is a number which is multiple of 3. So 3, 6. B is a number less than 4. 1, 2, 3. An even number greater than 4. It is only 6. Even a number not less than 3. Number not less than 3 means 4, 5, 6. Correct?
Sir,
No.
3 will also come.
Number not less than 3. Right? That didn't say equal to, no? Number 3 will come up. Number not less than 3. Think about it. Number less than 3 means, okay, 3 will come. Because, see, correct only. If I say f dash is number less than 3, then 1, 2. Then f will be how much? 3, 4, 5. Correct. So 3, 4, 5, 6. Right. So also find A union B. A union B another. A union B is sample space. 1, 2, 3, 4, 5, 6. Union null set is a sample space. A intersection B is null set. B union C. B union C is 3, 6. It is B only. E intersection F. E intersection F is the element 6. D intersection
Sir,
E.
B union C is C.
Either
You wrote it as B, sir. B
B
union
union
C.
C is C. Sorry. Yeah, B union C is C. Correct. So E intersection F is 6. Correct. 6 is common in both. D intersection E over. D intersection E is null set. A minus C. So what is there in A which is not there in C? 1, 2, 4, 5. D minus E. It is 1, 2, 3. It is D only. A number less than, E intersection F dash. E intersection F dash. What is it? It's a null set. Because E is 6, F dash is 1, 2. So F dash is 1, 2. Guys, is everyone clear?
Yes.
Okay. Right. So remaining problems, I'm expecting you guys to solve it. So 16.3 alone is left out. So tomorrow I might need 45 minutes of time. Okay. So spare it for me. We'll have somewhere around 4:30. 4:30 will work, right? Tomorrow.
Fine,
So
sir.
4:30 we'll have a session, and I'll complete the 16.3 so that we can wrap up math. Apart from that, on Sunday, if possible. Tell me.
Sir, could you simultaneously also do trigonometry? The equal.
That's what I'm saying. On
Solution.
Sunday, I will help you. You want me tomorrow itself?
Sir, Monday max exam, sir. So
I
need
know.
to-
Sunday, I will help you. I'll give you a technique on helping.
Sir,
All
is
right,
it
sir.
possible for doing tomorrow?
Trigonometry, you're talking about only one exercise, right? The solutions, right? Or is it the whole chapter you're asking?
That own exercise.
That one exercise only, that how to solve trigonometric equations.
Yes, sir.
That is just a 20-minute job for me. I'll do it tomorrow itself if possible. Provided
Okay.
you're not confused. You guys can handle a probability and trigonometry. I'm okay to teach. You can handle it, right?
Yes, sir. It's easy one.
Sorry, okay. Then I'll do it. So tomorrow, then we'll have a 1-hour session itself. And first 30 minutes, I'll complete this. The remaining half an hour, I'll teach you those things. So 4:30, we can have a session, right? So I'll see you all tomorrow. That's keep practicing.
Sir, when do we have chemistry classes this week?
I will tell you because I planned tomorrow, but I thought of taking math. I've asked teachers to record and give the content. So if math is over, right, I'll
Okay,
give those
sir.
math questions also to chemistry teachers. Okay, so they can take it.
Thank you, sir.
Maybe we can't help you for the pre-board, That is this exam that is coming up in the coming week. That is starting from Friday. Because I think physics will also be done by next week. I saw your schedule. So physics also, what I will do is